Hello, everyone, and welcome back to the 2023 CINR webinar. Now we're going to present topic area 3, fuels. And the first presenter will be Frank Goldner for FL1, accident tolerant fuels. Hi, Frank. I do have a few things that I just need to say before you start. Sorry about that. I just wanted to remind the participants that the overviews you are going to hear during this session are intended to introduce the topic areas and subtopic areas, provide context about the types of ongoing work that is happening in the Office of Nuclear Energy's programs and relevant technical areas, and provide guidance on areas that are clearly outside of the NE mission space. The presentations and the Q&A are intended to inform the applicants. You may choose to submit to this funding opportunity, not constrain those ideas to only those being pursued by the programs. The Q&A will be at the end of all of the presentations for the fuels areas. And with that, we'll turn the time over to our first presenter, Frank Goldner. Go ahead, Frank, when you're ready. Thank you.
Hi, welcome to everybody. I'm actually on annual leave, so my colleague, Donnell Gama, will cover the accident tolerant fuel area and turn it over to the others. But I'll be listening in and look forward to hearing what the questions. If you have questions, you can always contact the presenters or other people that are indicated in their presentations. Thank you. Don, please take over.
Thanks, Frank. Hello, my name is Donald Gama from NE42. Topic Area 3 covers 3 subtopics, as you know: FL1 fuels, FL2 trisulfur fuels, and FL3 metallic fuels. I'll be covering FL1, where Frank Goldner is the federal POC, but as Frank mentioned, I'll be providing his slides at this time. May I have the next slide, please? This slide covers the DOE team up with industry focused on ATF. The industry partners are Framatome, GE, Westinghouse, and GA. Oh, this is not the right, Julie? Oh, that's better, yeah. Okay. So this slide covers.
Sorry about that.
No, it's all right. The slide covers the DOE team up with industry focused on ATF. The industry partners, as you can see, are Framatome, GE, Westinghouse, and GA. Each vendor is pursuing their own designs, as example in this table. These technologies include coated zirconium claddings with and without doped UO2 pellets, use of fecal cladding designs, and SIG cladding and higher density fuels. DOE is supporting each vendor in their research, development, and qualification efforts related to their individual designs. DOE develops and maintains fuel testing qualification infrastructure, performs independent testing and evaluation, and specific tests and PIE as requested. Vendors have been exercising DOE facilities, including the Advanced Test Reactor, High Flux Reactor, Transient Test Reactor at INL, and the Severe Accident Test Station at Oak Ridge. Recently, Framatome has installed LTAs of their chromia-doped and chromia-coated concept at Calvert Cliff, and Westinghouse will be installing LTAs that will include both LU Plus and their coated design concepts in early next year, middle next year. Next slide, please. This slide provides high-level outline of suggested topic areas for university-led innovation that aligns nuclear energy research being conducted at US colleges and universities with DOE missions and goals. In practice, this generally means innovative solutions and a research that looks to enhance the state of the art for a particular physical phenomenon identified by the researcher. NE's ATF fuel cycle research and development provides support to the industry in 3 major areas: in research, development, and qualification efforts. One meaning to these terms are research, expanding the state of knowledge in a specific area by performing experiments, preferred and/or new evaluations of existing experimental data that create or expand existing models. Development may be implementation of innovative research concepts from an engineering perspective that incorporates integral effects, or the practical application of the innovative research. Qualification may be establishing safety-related performance boundaries or the demonstration of device processes, etc., to produce consistent outcomes of the required accuracy and precision. Innovative NEAR proposals are suggested to fall into the research category, advancing the state of physics for a specific phenomena under appropriate conditions, while recognizing the applicant's freedom to be innovative in their submission. For FY23, NE is requesting innovative research that enhances safety and performance in the following suggested areas. The applicant is suggested to include the specific area of research, a discussion of the challenge and innovation proposed, discussion of the appropriate figures of merits, etc., to characterize their proposal. For number 1, the ATF and LWO coolant chemistry and impacts on CRUD, David Anderson from LANL will be the technical point of contact. CRUD impacts may include dose increases, decreases in component service life, SIPs, and changes to thermohydraulic properties that may be of interest for innovative research. It is suggested that research to better understand how ATF materials can impact coolant chemistry, coolant impurities, additives, etc., that impact the formation of CRUD would be useful or to be considered. For item number 2, the ATF and power uprates, Mike Tudoso at BNL will be the technical point of contact. Power uprates have long been a part of the industry since at least the 1970s and use a number of approaches from margin recapture, equipment modifications, through to increase enrichment and battery loads. Plants have so far implemented measurement uncertainty recapture between 2 to 3%, stretch uprates around 7%, and extended power uprates around 20%, with EPUs requiring major modifications of the systems. It is suggested that the innovative research in how ATF with or without high enriched uranium, Lu+, and or high burnup may support uprates for the current LWR be considered. Major changes to geometry that will impact plant design are not encouraged. For number 3, how ATF can benefit SMR and advanced reactors, Nicholas Woolstenhume, forgive me if I've not said that correctly, at INL with a technical point of contact. Research that considers how current ATF concepts can benefit the unique requirements of upcoming reactor designs, such as NuScale, BWXT100, etc., in predicted normal and off-normal conditions are suggested. For item number 4, research that can support development of thick composites for ATF, for LWRs. That'll be led by, the technical point of contact will be Takaaki Koyonagi at ORNL. Research items or innovative items that can support development of thick composites through innovative NDE, non-destructive examinations for material characterization is suggested. For example, with thickness and uniformity measurements, process defects, etc. And number 5, research topic innovations that enhance safety and performance of existing LWRs. If you have any strong positions that you can submit to, that would be also applicable. The bottom line, however, is that the applicant is suggested to demonstrate the innovation through metrics that can be used to demonstrate success. Next slide, please, Julie. This is areas of less interest. As mentioned earlier, the suggestion is for NEOPS to engage universities for innovation areas that align with current DOE NE activities. As such, the following areas include topics that are of less interest: thorium fuel cycles, innovations that require major changes to the fuel assembly design and reactor coolant systems, liquid-based fuel, closed fuel cycles, etc. And with that, I'm done with my presentation. I'm going to open the door to Frank and Dan if they want to add anything to the discussion.
I don't have anything, thank you.
Thank you, Julie.
Hello, my name is Matt Hahn. I'm the program manager for the TRISO graphite program. This first slide provides some background on TRISO and highlights some specific areas of interest. As many of you probably know, TRISO particles are a fuel form that has demonstrated robust safety performance for high temperature gas-cooled reactor applications. Numerous US companies are pursuing the use of TRISO fuel in their advanced high temperature reactor concepts. And these include, as I will mention later, not just gas-cooled reactors, but some other configurations as well. TRISO-fueled reactors often use graphite as both a moderator and a fuel matrix material that consists of graphite and pyrolyzed resin. The following are potential areas of focus. I want to emphasize that these examples should not be considered bounded. Any proposals that conform to any strategic goals and would further knowledge of TRISO fuel manufacturing and performance would be considered responsive, even if they don't include any of the suggestions illustrated here. The first one I wanted to list is the fuel and fuel matrix properties. So if you know much about the AGR program that DOE has been performing for the past almost 20 years now, we have gathered and analyzed a lot of empirical data, and a lot of what we know about TRISO performance is based on that empirical data. As we move forward, industry is developing, I guess, different permutations or customizations of TRISO fuel elements that might differ from the exact specification from the AGR program. So with that in mind, there's a lot of interest in fuel modeling as opposed to repeating a long and expensive experimental fuel qualification program. To perform accurate modeling, we need to know more details about some of the fuel and fuel matrix properties, especially under irradiated conditions. A few examples are the pyrolytic carbon layers that bound the silicon carbide in the particles themselves, learning more about the pyrolytic carbon properties under irradiated conditions. And additionally, the graphite fuel matrix, learning more about its, for example, thermal conductivity, especially under irradiated conditions, are things that we could stand to know more about. Like all properties, you can look at a lot of different properties, but the ones that we're most interested in are the ones to which fuel performance is most sensitive. So keep that in mind. In addition to the properties, I would like to mention that we have a lot of novel non-gas cooled TRISO applications. I will list a few of those on the following slide. And so there are some things that we need to improve with regard to our understanding of TRISO performance in molten salt reactors and microreactors. And those new applications could involve some new fuel forms, including new fuel kernel compositions. If we go to the next slide, please. Thank you. Okay. As I mentioned previously, industry is producing a broad range of TRISO-fueled reactor concepts. The following is just a sampling of a much larger set of exciting work that is happening. X-Energy is being funded through the DOE Advanced Reactor Demonstration Award. If you keep up with the news, you probably saw the announcement yesterday that X-Energy and Dow Chemical will collaborate to deploy the XE100 technology at one of Dow's US Gulf Coast sites. So that's very exciting. Kairos Power is developing the Hermes TRISO-fueled reactor that uses a low-pressure fluoride salt coolant. BWXT is working on the BWXT Advanced Nuclear Reactor, and Project Pele, both of which are micro-reactor configurations that use TRISO fuel. The latter design is funded by the Department of Defense Strategic Capabilities Office. So that's sort of the industry-wide picture. Within the DOE's lab-directed work, the AGR campaign has and continues to hold critical importance. The current focus is the AGR 567 post-radiation examination, safety testing, and reporting to include NRC licensing reports. particular importance are the capsule 1 analysis to investigate particle failures that appear to have been caused by thermocouple issues. AGR 5, 6, and 7 are of particular importance because the fuel produced at pilot scale is similar to the fuel that would be loaded into a commercial TRISO-fueled reactor. Fuel oxidation testing is also a current priority. The AMIX furnace system will fill a key data gap in demonstrating fuel performance during accidents that air moisture ingress into the primary loop occurs. And as I mentioned earlier, graphite development is occurring in parallel with development of the fuel itself. Some key items here are the advanced graphite creep experiments and oxidation studies. The AGC experiments irradiate graphite samples under compression to induce creep and look at the radiation impacts there too. And again, as I said earlier, graphite in many TRISO-fueled reactors is not just a fuel matrix, but it's also a structural materials. And so many of these activities and potential proposals could address this function. Can we go to the next slide, please? Okay. Some areas not of interest. That first one I wanted to, well, really all of these I'd like to explain a little bit. Heavy ion irradiation is something that we struggle with sometimes because we need to be able to show its equivalence to neutron irradiation to have useful test results. So if you're submitting a proposal that includes heavy ion irradiation, please be sure to explain how we would be able to show equivalence to neutron irradiation. In addition, computer codes, we welcome proposals with computer codes, but keep in mind that we're looking for new work. So less interested in duplicating existing Parfum and Bison models, but enhancements, especially for critical phenomena, would be very useful. And this last bit, I think, it probably applies to all of the scopes. Please be mindful that we're looking for novel research rather than duplicating previous results. And I would encourage applicants to go to the NEAP website and ensure that you're able to distinguish what you're proposing relative to work that has already been done. And that's the end of my presentation.
Okay, thank you, Matt. Next, we're going to go on to FL3, the metallic fuels, with Ken Keller. Go ahead,
Hello.
Ken. Thank you.
All right, thank you. Hello, everyone. So in FL3, we're looking at metallic fuels, which generally apply to advanced reactors. So first, just a general broad overall expectations. If you're going to propose some concept, it needs to be manufacturable, have good economics, address safety, and address resource utilization. We'd like to see more efficient use of the fissile content. Not just one of those, all of those factors should be addressed. And the way we want to proceed, especially for closed cycles, is to see incremental improvements over the EBR2 reference fuel. So right now we could build a fast reactor with EBR2 fuel. It might have disappointing fuel lifetime, but we could definitely operate a safe reactor with the legacy fuel. And so that's our foundation, and then we want to work from there on incremental improvements. So we can break down the metallic fuels area into two broad categories. That's these two boxes on the left and in the center: open fuel cycles and closed fuel cycles. So an open fuel cycle means once through, you make fuel, you burn it, and then you toss it. So in that area, what do we want to see? What are we striving for ongoing in our programs? We're trying to optimize the fuel life and the energy output of that fuel. Also, since it's once through and we're not going to be reprocessing, breaking down the fuel, it's important that when the fuel leaves the reactor, it's storable, it's transportable, and it's disposable. So especially on the disposable aspects, chemically reactive or liquid bonds are to be avoided. Most repository concepts don't like the idea of, like sodium bonding or any other type of, so sodium bonding is at temperature liquid and it's chemically reactive. Over on the closed fuel cycle area, we're again looking at maximizing fuel burnup and fuel performance, just like in the light water reactor fuels. Even if you have closed cycle, you don't want to be shutting down the reactor and having to reprocess the fuel frequently. You want it to stay in the core and keep burning and minimize the times you have to shut down the reactor and shuffle or pull the fuel. Of course, closed fuel cycle fuel better have features that facilitate reprocessing. So there shouldn't be a feature that harms reprocessing. And there's multiple reprocessing technologies, so you have to be aware of that. We want to consider geologic repository burden minimization. That often means the fuel will carry forward certain activation products to continue to be burned, the transuranics, for example. So your fuel design has to incorporate the performance, both neutronically and chemically, mechanically, of these constituents. In closed fuel cycles, fuel clad bonding of reactive materials or liquid materials is acceptable because just consider that fuel clad bonding, its interaction with the reprocessing process. And of note, in metallic fuels modeling, we're more interested not in computer code, but the modeling like Isaac Newton did, modeling, orbital mechanics, coming up with the mathematical concepts and the physical principles. So we're interested in first principles, predictive capability, design streamlining. For example, alloys and cladding. It'd be great if we could have some modeling that would break through and get us out of the trial and error for cladding. And licensing support, of course. All these fuel concepts should be striving towards a future licensing. So that's it for that slide. The next slide is just talking about ongoing work. The weakest thing in metal fuels tends to be this cladding. So cladding life extension gets high interest. Current technologies are being proposed are getters, things that in the fuel meat pull out the bad constituents that end up migrating to the cladding and causing harm. Liners to the cladding. A liner can maybe be mechanically inferior to the cladding material, but perform a protective service. And of course, conceiving and optimizing cladding materials, it's an infinitely complex field of alloys. Even if you name Fekrol, but there isn't just one Fekrol. There's all you modify the constituents within it. So that's ongoing work. Manufacturing, fuel slug fabrication. The old EBR2 way was very wasteful, using glass forms. So any improvement on that's great. Once through, fuel concepts, especially that have to avoid bonding, are quite often looking at co-extrusion technologies, extruding multiple materials. Cladding material fabrication. Some of these cladding materials defy fabrication. We can get the metal, it has neat properties, but we can't get it in a shape or join it the way we need to. ODS steel is an example. Testing without a fast reactor. The United States does not have a fast reactor that we can use. VTR process is currently on the rocks. So we're looking at testing out of pile, doing separate effects testing. In pile, we use shielding to shield out thermal neutrons. There's also the FAST program. We use miniaturized, accelerated samples. Miniaturization kind of alleviates that shielding of the thermal neutrons, and also playing with the enrichment in our fuel samples can also accelerate the testing. Instrumentation, we're working on test vehicles to test these advanced fuels in the unique coolants that they have, both for steady irradiations, for example, in the advanced test reactor, and transient testing. And HIFER reactor also is used, and that's a very small reactor, so there's also an interest in very small test vehicles. Models expanding into the advanced reactor fuel realm is just expanding the existing models to take on the advanced physics and characteristics. We have a balance. We're okay. We look for searches for engineering solutions using an efficient balance of empiricism and modeling. You don't have, if you have a cheap empirical way to get data and do research, you don't need to spend a lot of money on modeling, and vice versa. If you have expensive experimentation needed, modeling can really pay off. So that's our ongoing work. Next slide, please. Here's some areas that we have less interest in. Technologies that are related to the thorium fuel cycle. Thorium fuel cycle is technically viable, but like as a friend told me, he's like, we have plenty of uranium. When the world starts running out of uranium, then we can take on the more challenging thorium fuel cycle. No need, so it's a low priority here for us. We're not interested in propulsion fuel concepts, for example, nuclear rocket motors. We're not interested in new propulsion concepts. The once through open cycle metal fuels are currently of higher interest because there's some commercial interest in those rather than a closed fuel cycle. However, we want to steady, continuous contributions and improvement in the advanced closed cycle fuel concepts. That's ultimately going to be where we need to go if we do go nuclear, because closed fuel cycles what maximizes the fuel resource utilization. We're also not interested in any concepts that propose enrichments greater than 20%. That's due to regulatory limits. As mentioned in the previous presentation, ion beam irradiation is not yet a proven tool. However, it is promising. So if you want to propose using heavy ion beam irradiation, your proposal should address the current state of the art and address all the non-prototypic aspects in the scope of work. How are you, what's the state of the art? How are you going to address those non-prototypic attributes? And I believe that's it for my slides. Thank you.
All right, for the other fuels topics, much like the other areas, proposals that are relevant to fuels as described in this topic area can be submitted to the other fuels topic area. So as long as they meet the intention of any mission, which is outlined in these 4 bullet points, and a strong case is made for why those topic areas are relevant, those would be considered in this other fuels topic area, FL4.
Okay, and we will move into questions and answers. And as a reminder for attendees, if you have questions for any of these 4 work scopes, you are welcome to type them in your control panel under the questions section. So I'll begin with an overall question for topic area 3. Are proposals that make use of fusion neutrons for nuclear fuel processing, so either TRISO or metallic fuels, acceptable for this topic area?
I'll take a stab at it if no one wants to talk. Fusion is out there, and by the way, no, because fusion does not have excess neutrons. They need to use every neutron to breed tritium. So I even if it was around the corner, I don't see a concept where a fusion device is going to have excess neutrons. If that's the correct interpretation of the question, there is not an interest.
Thank you for that, Ken. Another question I think that is overall, is advanced manufacturing of claddings like Fe, Cr, Al of interest?
Absolutely, we have a lot of work to do in these advanced cladding. So any advancement in the cladding production technologies is welcome.
Thanks again, Ken. I do have a question for FL1. Does this work scope encourage computational model validation or experimental validation for the proposed projects?
Hi, I think tomorrow there is a discussion on extending validation of models for codes. But for this work, what's preferred is developing the actual experimental data that models can be validated to, or developing new models based on better interpretation of experiments or and things like that. Does that make sense? So we're not looking for code development. We're looking for, I believe, Frank or Dan can pop in anytime, but we're looking for model development that's generic or that can be applied to understand the physics of what's going on for a specific phenomena that is of interest for that research topic. I hope that answers.
I would add that I think modeling can complement experimental work. So it has a role, but it shouldn't be just the sole activity.
Yes, yeah, that's right.
Okay, thank you, Frank and Don. And to follow up on that, as Don stated, there is a topic area 4 presentation tomorrow for modeling and simulation, and that is the verification and validation uncertainty quantification. That presentation will begin at 10 a.m. Eastern tomorrow, August 11th. Moving in, let me address another FL1 question that just came in. Are proposals relevant in areas of longer term or near term ATF options, considering the fact that long-term ATF data availability is an issue? For example, silicon carbide composite cladding.
I think the answer is yes, because that is actually one of the topics in slide 2. Was it slide 2 or slide 3? For development of SiC composites for accident tolerant fuels for LWRs and advanced reactors. So that was topic number 1, 2, 3, 4. So I'd say the answer is yes.
Thank you. Another FL1 question. Are proposals based only on simulations acceptable to the FL1 work scope to analysis reactor uprates?
Yeah, I would imagine that we wouldn't be able to do. Well, yeah, I would agree that would be the case. Frank or is Tom? If Tom Dodoso was on the line, they can add, but I don't see an issue with that. As long as you're very clear on the phenomena that you're targeting with the ATF design, I think that would make sense.
Yeah, I agree that makes sense. And that's the type of question where we've given you the name of Mike Dodoso, you can discuss that with him, because clearly how you simulate core behavior may be valid.
I believe Michael Dodoso is here with us. Michael, can you unmute to help answer the question? I think he's here and he unmuted, but we are not hearing him. Okay, I guess we'll move on. Thank you.
The next question is related to one I believe I just asked, but it's in regards to FL1 and the call. Does it encourage the use of existing DOE NE code suites for the proposal or any validated commercial software?
Yeah, I would agree with that. As long as you demonstrate, your basis appropriately, I think that's fine.
All right, moving into FL2. Is TRISO disposal or performance in long-term storage conditions relevant to this topic area?
I would say that generally, no, because the TRISO fuel particles, compacts, and pebbles we consider those to be repository ready. I think Paul Dempowitz may be on the line. If you feel you have anything to add, feel free to jump in.
Paul, can you unmute?
So can you hear me?
Yes, we can hear you.
Yep. So yeah, I agree with Matt that we had talked about this earlier, and in terms of like reprocessing the TRISO particles, that's something that we're not really into at the moment, but I wouldn't necessarily reject a proposal on the impacts of repository storage on TRISO particles. I mean, I think that's still important. So I don't know, Matt, what do you think about that? But
I think, yeah, with repository storage, I could see how that could be relevant.
yeah, it's really more the processing of the particles that is not something that's of interest at the moment.
Hey, thank you all. Another question for FL2. Is there any interest in technology development that could speed up TRISO fuel characterization, but the technology hasn't been implemented for use with irradiated materials yet?
That that sounds like that. It sounds to me like that could be relevant. Absolutely. Again, Paul, if you'd like to add anything.
I agree with Matt.
Thank
I think
you.
that's relevant. In the U.S., the AGR program at INL and Oak Ridge have developed PIE methods for particles, advanced those in certain cases, but I mean, there's still room for, further advancement. So I think that does make sense.
Thank you. Another FL2 question. For the fuel oxidation testing of TRISO, could you give us an idea of conditions that would be relevant? So specifically temperatures and maybe oxygen moisture concentrations?
I'd love to defer to Paul on this one if you're able to provide anything off the top of your head.
Yeah,
I can't.
I apologize. Could you repeat that question?
Yeah, the question was for fuel oxidation testing of TRISO, could you give us an idea of conditions that might be most relevant? So maybe like specifically temperatures or oxygen moisture concentrations, such as high, low, or trace?
Yeah, I don't think I can do that in 30 seconds on this call. I'm not sure how DOE wants to handle that in terms of like providing more information on some specific conditions. I know that there's lots of information out there, at least on the established designs for, bounding conditions of oxidant ingress during accidents. For some of the newer designs, it's probably not out there, but I think that information is generally available. I'm willing to put together some more information if the sponsor is willing to, have that in like a Q&A document or something.
To build off of what Paul, this is Drew Thomas, by the way, to build off of what Paul's saying, I would encourage the applicant to submit that question by email at nup@inl.gov. That way we can process through a full question and answer. There's also a reminder that we're continuing to plan additional opportunities to engage program contacts to be able to better understand some of these questions. So there's some ways to continue having these dialogues after this webinar is finished.
And another question for FL2, is there interest in MOX or just uranium only kernels?
Not aware. Oh, go ahead.
Yeah, this is Paul. We have never talked about MOX before, so I would say at this point it is not of interest.
Okay.
That's pretty much what I was going to say. I don't have anything to add.
Okay, great. I have some questions for FL3, so moving into that area. For FL3, is cost-effective manufacturing or fabrication of ODS steel cladding tube relevant?
Yes, it's highly relevant. That's a real Everest right now. That's the prime example of manufacturability. We can make ingots of ODS. It takes all kinds of mechanical working to preserve these oxide dispersions in there. It's a real challenge to get a shape we need. So highly relevant.
Thank you. For that same work scope, FL3, are both experimental and modeling work relevant for this area?
Absolutely. As I kind of said in the briefing, there are some phenomena that challenge our first principles understanding. So there's two paths to go when you don't understand the first principles. You let it go, you give up, and you do empirical work. That's acceptable in our field. And the other direction is you dive in and do fundamental basic like separate effects testing, trying to get those fundamental principles. Both are relevant, and it's a judgment call. We can't do empirical and modeling on everything, so it's a judgment call, case by case. But yes, definitely relevant.
Okay, thank you. Jumping over to FL1, are uranium carbide and uranium nitride of interest or relevant for this work scope?
Yes, I believe those are long-term subjects that are of interest.
Okay, thank you. It looks like we're wrapping up some of these questions. So I do have a couple of, oh, here's one that just came in. In FL2, FL3, as part of advanced manufacturing and development of FECRAL claddings, can simulated ion irradiation testing be a part of the work?
It can definitely be part of the work, but as we said, that the technology of ion radiations is far from established. As far as it has massive non-prototypic aspects that must be addressed in the proposal.
Okay, a follow-up question to FL2 came in. If the characterization technology was focused on measuring thermal conductivity of diffusivity, would that increase its relevance?
Yes, this is Paul. The main area where we're interested in thermal properties is the matrix itself, the bulk matrix. There are some interesting oddities, I guess, about the thermal conductivity of matrix that happens when you embed particles and you get a very oriented microstructure around the particles. And we really don't have very good data on the modern matrix formulations and what their thermal conductivity is. So that's kind of the main area. There's been discussion in recent months about thermal conductivity of the coating layers. The issue there is just that it's got a very small effect on particle temperature and performance. You know, those are very thin layers. The temperature drop across them is very small. And in modeling, in some sensitivity studies that we did in the AGR program, it showed that, you know, you can vary some of those properties by an awful lot, a factor of like plus and minus 3 and 5. And, you know, it didn't affect the outcome of the failure prediction. So, yeah, I guess the answer is yes. If you're looking at matrix, thermal properties is kind of one of the prime areas that we are interested in.
Thank you for that answer. The next question is for FL3. Following on the ODS manufacturing question, will a proposal be considered relevant if the newly fabricated ODS are not irradiated?
Could you repeat that question?
Yes, I can. So this question follows on the ODS manufacturing question that was asked earlier. And so the follow-on question is whether a proposal would be considered even more relevant if the newly fabricated ODS is not irradiated.
Okay. We definitely like to see a radiation testing associated with things. In this case, though, just doing basic, what would have to be established in ODS manufacturing is the microstructure, the maintaining that ODS distribution microstructure. So you should manufacture and have a diagnostic or testing. It could be electron microscopes or something to demonstrate that you have succeeded, that you've maintained that ODS structure. So yeah, I'd say in that case, the radiation testing wouldn't be needed. Definitely measuring the maintaining of the, I'm repeating myself, the oxide dispersal, maintaining that. That's it.
Yeah, this is Dan. Just to add to that, I think it would be worthwhile to identify the pathway to irradiation as part of the proposal, not necessarily implementing it.
Okay, at this point, we don't have any more work scope specific questions, but we do have two general questions. And the first one is, if a PI submits two proposals to the same scope, perhaps one as PI and the other as co-PI or collaborator, will it affect the chances of selection?
And Anna, this is Drew Thomas. I'll take this question and the other general questions. There's no prohibition on submitting more than one application to the same topic or subtopical area. You have the ability to do that. The one exception to that is the applications that are submitted need to be substantially different from each other, meaning that they should be different scopes of work, different proposals, so to say. And there's no, it doesn't have a bearing on the selection of applications. All applications go through a merit review process and are recommended based on that merit review process.
Okay, another general question here is if the scopes in this call have a technical point of contact.
So you notice in this presentation that there were some technical points of contact who answer questions here on this call or identified in a presentation. The draft work scopes do not have technical points of contact listed. The reason for that is they're relatively broad, and some of them are very broad, and there are multiple different technical points of contact that could potentially provide feedback or answers in different formats. So we have not provided those individuals. We'd encourage you to reach out to the NEUP office at neup@inl.gov or the federal program managers as those central points of contact.
And we have one more general question, and that is whether pre-applications could address more than one work scope. So for example, if somebody wanted to submit an application to FL1 or FL2 along with submitting to NM3, which is an advanced nuclear materials work scope.
So if I'm understanding the question correctly, I'm interpreting that to mean one application that is cross-cutting through several different topical areas, and the applicant is responsible for choosing the most relevant topic area in that from that standpoint. So it's really a judgment call from that perspective about which topic area does it most focus on, and if there's questions, curiosities, or concerns about that, that's a question that can be extended to the NEUP office for clarification about how the other scopes work and how the other topic areas are, so we can do our best to direct you in the best way possible.
And Drew, is there a precedent for swapping the application among the topical areas? Should one group say we're not interested, this might be more relevant? I think I've experienced that. I think I've received.
Yeah, that's a good point, Ken. The DOE does reserve the right, with an applicant's permission, to move a pre-application, for example, into a different topical area that is determined to be more relevant, for example. So there is a process that we can go through to do something like that. So that's another reassurance maybe, and thanks, Ken, for pointing that out, that as applications are being reviewed, those types of discussions happen, and with PI concurrence and approval, those types of changes can be made after the pre-application submittal. Are we finished the questions? Okay. I would like to just mention to everybody, there were a lot of really good, very specific questions in this session. Trying to understand where the program focus is and everything else. I do want to emphasize that it's intentional that we have an other fuels topic area and an other area in every single one of these topic areas to capture things that may be of lower interest to the programs, but still meet the intent of any mission space. And so I think the discussion was great here. I hope that through other engagement activities, we'll continue to have more discussions and more specific discussions to better understand what the programs are currently doing. But I just want to emphasize that there is that other fuels topic area for a reason, and that is to try to capture new, innovative, different ideas that may not come through as part of our part of the traditional process. So with that, I'll turn the time back over to Julie. Thanks, everyone.
Okay, everyone, thank you for attending today. That's the end of the topic area 3 fuels presentations.